The restrictions in the United States proved even harsher. For nearly 80 years, government regulation and industry lobbying efforts made the use of hemp extremely difficult throughout the country. The Marijuana Tax Act of 1937 did not completely outlaw hemp, but it introduced restrictive tax stamp requirements that were nearly impossible to secure. The American hemp sector, once among the nation's most heavily cultivated agricultural industries, collapsed with shocking speed. Many observers believe powerful industrial interests played a major role. William Randolph Hearst, whose financial interests included large timber holdings and paper manufacturing operations, used his newspaper empire to push a campaign against hemp. Public perception was intentionally shaped by connecting industrial hemp to the psychoactive reputation of marijuana. In 1970, the Controlled Substances Act transformed that suppression into a complete federal prohibition. For the next 48 years, American architects and engineers could face federal criminal penalties simply for possessing hemp hurd. During that same period, builders in France and Britain continued refining national standards and testing hempcrete inside commercial high-rise construction projects. The United States, meanwhile, remained trapped inside a legal blackout. When federal law finally shifted in 2018, the American building industry had already spent decades centered around fiberglass insulation, spray foam systems, and the supply networks and workforce training built around them. Hempcrete entered the market with no domestic testing history and no established position inside national building codes. Adoption faced major obstacles from the beginning. That barrier finally changed in 2024. The International Code Council officially approved hempcrete for inclusion within the International Residential Code. For homeowners seeking natural insulation with strong performance characteristics, hempcrete became a serious option. Still, several important limitations must be understood. Despite the name, hempcrete is not structural concrete. It cannot support foundations or roofs under load. Instead, the material functions as insulation and infill placed inside a structural frame, most commonly timber. Anyone replacing conventional insulation with hempcrete must also redesign the wall assembly to remain vapor open. Materials such as OSB or plywood should generally be avoided because they can trap moisture. Wood fiber boards or direct lime plaster substrates are preferred alternatives. Producing hempcrete independently remains possible, but prefabricated hempcrete blocks are currently the easiest entry point for most buyers. Companies such as Hemp and Block in Colorado now manufacture these products domestically. Customers can order them online without hiring specialized contractors. The blocks arrive fully cured, eliminating the 6 to 12-week drying process associated with traditional cast-in-place applications. There are also retrofit blocks with notch designs sized specifically for standard 2x4 and 2x6 stud framing. That allows insulation upgrades inside existing walls without tearing down the entire structure. For larger developments, prefabricated wall systems are now available from companies including Homeland Hempcrete in North Dakota. These panel systems can shorten wall construction time by an estimated 75%, allowing a standard house shell to be assembled within only a few days. Builders pursuing full monolithic wall performance can also turn to companies such as Marie-Chanvray in Pennsylvania, which controls advanced spray-applied hempcrete technology. At present, hempcrete construction generally costs around 10 to 20% more than traditional stick and bat methods. However, that price difference continues shrinking as regional supply chains expand. Long-term operational savings also help offset the initial investment. Heating and cooling expenses can drop by as much as 50% over time. Current federal tax policy additionally allows homeowners to claim a 30% tax credit for qualified insulation expenses. One of the strongest examples of this emerging industry can be found in Minnesota through the Lower Sioux Indian Community's Seed to Sovereignty program. The community constructed its own $2.3 million processing facility and currently cultivates more than 120 acres of hemp on reservation land. Their goal is to build hundreds of hempcrete homes for local residents. Community leaders estimate these homes will reduce energy expenses by 70% compared with standard housing, while also creating significantly healthier indoor environments for families. The history of hempcrete demonstrates that revolutionary technology does not always have to be modern. This material is more than 1,500 years old. It removes carbon from the atmosphere, gradually transforms into stone, and helps protect the health of those living inside its walls. For 80 years, it remained pushed aside and largely forgotten, not because it failed, but because it threatened the profits of larger industries. If preserving knowledge about self-sufficiency and sustainable construction matters to you, continue exploring and sharing information like this so these techniques are not lost again. And if you are interested in another historical building method, there's also an ancient Japanese technique that makes timber resistant to both fire and rot. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one. There is a construction material that resists fire, absorbs more carbon than it releases, and continues gaining strength year after year. Studies have repeatedly shown that it can reduce energy costs by more than 50%. Yet in 1970, the United States government classified contact with this material as a federal offense. That material is known as hempcrete. Today, it stands as one of the most unusual and promising building technologies available. So what exactly makes it so important? Why did major industries work to push it out of public view? And how could it potentially save homeowners thousands on utility costs today? The modern resurgence of hempcrete began in 1986. An artisan named Charles Rossetti received the assignment to restore Maison de la Turque, a historic structure located in the French commune of Nogent-sur-Seine. Rossetti encountered a problem that had frustrated restoration specialists for centuries. Conventional masonry was gradually damaging the building itself. The ancient timber framework naturally expanded and contracted as humidity and temperature shifted, but the stone and brick filling inside the structure remained rigid and immovable. That mismatch caused fractures throughout the masonry. Moisture became trapped against the oak supports, leading the wood to decay and putting the entire structure at risk. Rossetti approached the issue differently. Instead of relying on stiff stone or standard concrete, he experimented with a mixture created from the woody intersection of the hemp stalk known as hurd. He blended the hurd with water and a lime-based binder, producing a lightweight material that remained breathable and flexible. Rather than resisting the wooden frame, the material moved with it. The outcome was dramatic. The old beams finally dried, the framework stabilized, and the building was preserved. Although Rossetti is associated with the modern revival of hempcrete, the methods behind it were far older. Lime and hemp mixtures date back more than 1,500 years. Evidence shows they were used during the 6th century on the Merovingian Bridge in France. In India, archaeological research at the Ellora Caves, recognized as a UNESCO World Heritage Site, discovered hemp fibers incorporated into earthen plaster inside Cave 12 as early as the 6th century AD. Ancient builders understood the advantages clearly. Hemp fibers strengthened the material and helped prevent cracking. The plant's natural resistance to insects also protected sacred artwork through centuries of monsoon weather. To understand why hempcrete is so different from conventional materials, it is necessary to examine its entire life cycle, beginning the moment it is installed inside a wall. The process starts with hemp hurd, which is essentially an industrial leftover. After the long fibers are removed for textiles, rope, or clothing, the remaining woody core is usually considered waste. Under magnification, the hurd reveals a dense network of tiny air chambers and tunnels. This cellular structure is exceptionally effective at trapping air. The hurd is then combined with water and a lime-based binder. As moisture leaves the mixture, the material begins to solidify through what is known as the carbonation cycle. Unlike Portland cement, which hardens rapidly through hydraulic reactions, the lime inside hempcrete gradually absorbs carbon dioxide directly from the surrounding atmosphere. Over time, the lime chemically reacts with the carbon dioxide and transforms back into calcium carbonate, the same mineral found in natural limestone. In effect, the wall slowly turns into stone around the hemp particles. The mineral structure becomes naturally resistant to combustion while steadily increasing in density over the years. This petrification process can continue for as long as 12 years after installation. A wall built today may therefore become harder and more fire-resistant a decade later than it was immediately after construction. Few modern insulation materials can accomplish both objectives at once, removing greenhouse gases from the atmosphere while simultaneously increasing durability. The wall system is also vapor permeable and hygroscopic. Instead of trapping moisture, it allows humidity to move through the structure naturally. As a result, indoor humidity levels tend to stabilize between 40% and 60%. Researchers studying indoor health consistently identify this range as ideal for human comfort. Conventional American construction often depends on costly mechanical dehumidification systems to maintain those conditions. Hempcrete achieves the same effect through the wall itself. One of the biggest misunderstandings surrounding hempcrete comes from comparing it to fiberglass or spray foam using R value alone. Hempcrete delivers a steady-state R value of roughly 2.0 to 2.5 per inch. That figure is lower than several synthetic insulation products currently on the market. Hempcrete functions through two separate systems operating together at the same time. The trapped air inside the hurd's microscopic structure provides insulation. Meanwhile, the hardened mineral body of the wall behaves as thermal mass. During the hottest hours of the day, the wall absorbs heat. As temperatures fall later on, that stored warmth is slowly released back into the structure. A standard lightweight wall stops performing once the inside temperature matches exterior conditions. Hempcrete behaves differently. Even after the heating system shuts down, the wall continues regulating temperature for hours. This follows the same concept used in traditional adobe construction, though hempcrete combines that thermal behavior with far stronger insulating capability. There is also another major advantage. The lime binder maintains a pH level near 12 throughout the entire lifespan of the structure. That highly alkaline environment is deadly to mold, which requires much more acidic conditions in order to grow. Under laboratory testing, researchers exposed hemp mortar to continuous high humidity for 1 full year. No mold growth was detected at all. The same chemical properties also create strong resistance against pests. Silica inside the hemp hurd discourages rodents. Testing conducted at the University of Hawaii against Formosan subterranean termites showed that mineralized hempcrete produced far higher termite mortality compared to traditional Douglas fir controls. In regions known for severe termite activity, including Australia, entomologists observed that termites had almost no impact on the material. Laboratory data is valuable, but the strongest evidence appears when hempcrete is used in real construction projects. In 2012, the British retail corporation Marks & Spencer opened a 195,000 square foot location in Cheshire, England. The structure used prefabricated hempcrete wall systems. Post-occupancy monitoring showed the building consumed 42% less energy than a comparable conventional structure. Heating fuel demand was also 60% lower than the company's own engineering projections. During winter conditions, the building lost less than 1 degree Celsius of heat overnight. A typical retail building would normally lose closer to 9. In the United States, the first approved hempcrete residence was completed in Asheville, North Carolina, in 2010. The property, called the Push House, measured 3,400 square feet and used 12-inch hempcrete walls throughout the structure. Monthly cooling expenses remained below $100. That represented a 60% decrease compared with similar homes nearby. The homeowner also reported a substantial reduction in insurance costs after the provider examined the wall system's fire resistance performance. That fire resistance received major confirmation during a landmark American test conducted in July of 2024. A 12-inch spray-applied hempcrete wall underwent exposure to 1,700 degrees Fahrenheit for 60 minutes while carrying structural load inside a Pennsylvania testing facility. The wall passed the fire test successfully. It also endured a following high-pressure hose stream evaluation. Throughout the entire 60-minute exposure, temperature sensors on the opposite side of the wall recorded almost no increase in heat. While the fire-facing side experienced conditions capable of destroying fiberglass and converting spray foam into toxic gases, the exterior surface remained near ambient temperature. In standardized flame spread and smoke development testing, hempcrete achieved a score of 0 in both categories. Previously, only mineral wool had reached the same result. The advantages of hempcrete extend far beyond individual savings. Hemp acts as an extremely efficient carbon sink. Within a single 100-day growing season, the plant can reach 15 feet in height while absorbing roughly 9.8 tons of carbon dioxide per acre. Because the construction process utilizes the hurd, which would otherwise be discarded or burned, the captured carbon becomes locked inside the building for the lifespan of the structure. Peer-reviewed life cycle studies consistently conclude that hempcrete walls produce a carbon-negative footprint. In other words, they store more carbon than was released during manufacturing. For an average residential build, this can permanently remove several tons of carbon dioxide from the atmosphere. Considering its safety profile and efficiency record, it seems remarkable that hempcrete has only recently begun entering mainstream construction. Across Europe, adoption has gradually increased. Though progress remains slow despite the material's clear advantages over conventional methods,